In this example, we will antidifferentiate x times the square root of 1 minus x to the fourth. Now, looking at the integrand we have with the 1 minus x to the fourth underneath the square root, it is not immediately clear that we can apply a trig substitution. But a few factors here might actually indicate a slightly different approach to start. Seeing that x dx and an inside function might indicate that we could think about a substitution. So could we somehow come up with a choice of u so that our du is x dx? Well, with that observation, we note that yes, we certainly can, because x to the fourth is really x squared squared. So we can use the substitution u equals x squared, so that du equals 2x dx, or equivalently, this would imply that 1/2 du is x dx. So rewriting in terms of our variable u, we would have 1/2 times the antiderivative of the square root of 1 minus u squared. And now that we've made this initial substitution, looking at our integrand, we are very well suited to apply now a trigonometric substitution. 1 minus u squared indicates that we would like to let u be equal to, in this case, 1 sine theta. So u is sine theta, and du is going to be cosine theta d theta. So now applying our trigonometric substitution, we have the 1/2 out front, then we have the antiderivative of the square root of 1 minus sine squared, and the du becomes cosine theta d theta. And now applying kind of the corresponding trigonometric identity, note that 1 minus sine squared is really cosine squared, and our integrand is made up of the square root of cosine squared, which is cosine, multiplied by cosine. So we end up back at this familiar function to antidifferentiate, cosine squared. Rewriting in terms of the half angle formula, we'll have 1/2 times 1/2, that extra 1/2 that comes from the formula, and then cosine squared is what? 1/2 times the quantity 1 plus cosine 2 theta d theta. Anti-differentiating term by term, 1/4 times the quantity theta plus 1/2 sine of 2 theta. And keep in mind that we're going to draw a right triangle here to kind of get from thetas back in terms of this variable u. In order to do so conveniently, it's nice to rewrite that sine 2 theta in terms of its double angle formula, 2 sine theta cosine theta. Doing so, this becomes 1/4 theta plus 1/2 times 2 sine theta cosine theta. And now we would like to draw a right triangle here so that we can rewrite in terms of the variable u. So we have that u is equal to sine of theta. So if we draw that associated right triangle, so if u is equal to sine of theta, so we would have u, and the hypotenuse would be 1. Then by the Pythagorean theorem, that bottom leg would be the square root of 1 minus u squared. So putting this all together, we have the 1/4 hanging around out front. If sine of theta is u, that means theta is arc sine of u. Plus, we have sine theta, which is u, cosine theta, square root 1 minus u squared, and then this is all plus c. So we've solved the trigonometric integral, we've used the right triangle to rewrite in terms of the variable theta, or excuse me, in terms of the variable u, but remember the original question was phrased in terms of the variable x, so we need to use the original u substitution. and just resubstitute here. Make each of these u's into an x squared. So 1/4 arc sine of x squared plus x squared times the square root of 1 minus x to the 4th, all plus c. So once again, a big picture observation to make is that many integrals require multiple techniques of integration. And here we see an example where we first apply a u substitution so that we can then apply a trigonometric substitution. Once you solve that resulting trig integral, you rewrite in terms of u, and then you rewrite in terms of the original variable x.